let's look at some examples of calculating signal power and energy. These are examples in addition to your textbook, so if you haven't already, please be sure to review the examples there. One that I want to take a closer look at is the power of a sinusoid from a signal sense. So if we have a sinusoid, here I'm showing a sine wave, but this will work for a cosine or any phase shift that goes on forever. We know that we have a infinite amount of energy, but power average is going to be finite. And your book goes through the calculation of this with the trig identity and so on. But this is an important result, and similar results are going to be useful to us later in the course. So I want to take a look at what's going on here in a little more detail. So for a sinusoid, and like I said, even though this one shows 0 phase shift, this would apply for any phase shift. I have a period t0, and I have an amplitude to the peak here of A. So now we want to know what is the power of that. And if we look at the definition of power for a periodic signal, we don't have to go out to infinite time. Remember, we can just look at the average over one period of the energy and then divide that by the time, which is just the period. So first of all, let's take a look at what's happening here. So if I look at magnitude of that original sinusoid and I square it, what's going to happen is when I start at 0, so it's going to be at 0, and then it's going to go up to a peak, and it's going to come back down to 0 at the first 0 crossing. And then where it reaches the trough at 180 degrees after the start, I'll be up to another peak again. And what's going to happen is the frequency doubles. So our original T0 up here, we went from 0 crossing to 0 crossing. That was T0. It's a little bit mislabeled here. T0 to T0, that would be one period, or peak to positive peak, that would be one period. So by the time we got through one period, though, we actually met two maximums in the square, because this causes a maximum and this causes a maximum. So if we look at it that way, here is our original T0. So that's T0 of the original sine wave. So that's why when you square a sinusoidal function, you end up getting twice the angle, because this the square goes through twice the number of cycles. That's one interpretation of the trig identity that the book uses. Now, this integral here says this. It says take the area in one period of this squared function and then divide it by the period. So we're going to take the area. And another thing that is very useful that actually comes out of the trig identities is the area here is the area under the curve over one period. And I'm just drawing a straight yellow line going across at amplitude squared. So the area is the area under the blue curve. And by symmetry, we could show, and using trig identities which exploit the symmetry, that that yellow shaded area is actually the same as the area above the blue line and below the a squared line. So that area, that yellow shaded area, which is the integral that we're evaluating, is going to be half of the area of this yellow rectangle right here. And so our average power, if we take a look at it geometrically like that, is going to be 1 over T0. We just carry that over from the expression on the left, and then it's half the area of the rectangle. So half the area of the rectangle has base or duration t0, and it has height a squared. So the t0s cancel out, and we end up with a formula I hope you remember from circuits, which is the average power of a sinusoid is amplitude squared over 2. So this is a geometric interpretation. Your book goes a little more formally through a trigonometric interpretation, but they are equivalent, and being able to visualize what's happening with the power with the sinusoid is going to be useful to us later in the class. Okay, let's do one last example. Let's look at power and energy of the step function. So we have the step function, and we want to know its power and its energy. So the energy is going to diverge to infinity because the energy says you take the integral over all time, negative infinity to infinity. Well, I can simplify and start at 0 because I'm not getting any area there. And I integrate 1 squared dt. So the energy just keeps adding up, and this diverges to infinity. But we can still take a look, and see, we would expect it to be a power signal. So and actually let's make it amplitude A, and that'll be A squared. Okay, so now let's look at the power. The average power, this is not a periodic signal, so we have to do the limit as t goes to infinity of that value, divide by the value t, and go from minus t halves to t halves. The unit step, so we have A times the unit step, magnitude squared. It's never a complex number, so I can just square it here. And we integrate with respect to time. So first thing we do, let's make a couple simplifications. First thing we do is we see that the value of the function is 0 until 0. So it's for negative time, it's 0. So I don't actually have to evaluate the integral there. I just need to evaluate it starting at 0 up to t0 over 2. Now, we break this integrand down. We see we have an a squared term, and we have unit step squared. The unit step is 1. I square it, I get 1. So that's all I have left. So when you have a function that has piecewise segments like this, it's very useful to break it up into its parts when you're evaluating the integral. So I have the part before time 0 and the part after time 0, and they each get a simpler expression. So now I have to evaluate this. The integral here is of a constant. So let me pull that out. I have the integral from 0 to t squared, t over 2 of 1 dt. So if I simplify that, I have t over 2. And now the t's cancel out. So I do that cancellation before I consider the limit as t approaches infinity, and I end up with a squared over 2. So what happened was, if it were just a DC value, we know that we would expect the power to be amplitude squared or voltage squared, and we're assuming a normalized resistive value of 1. But since for the first half of infinite time, the signal was off, it's not contributing to the power during that time. It's only contributing to power during the second half of the infinite time. So that is the result for the unit step. The power is a squared over 2. Now, it turns out that if I delay the unit step to any positive or negative finite amount of time, and I go through the integral, the analysis will be just a little more involved, but I will get out the same value, a squared over 2 for the power, when I take that limit as time goes to infinity. So try that yourself if you want to try a shifted version and see what happens to the integral. You'll get a vanishing term, and all that will be left over will be a term that reduces to a squared over 2. So that's a key tip for this section. When you are evaluating power and energy for a function that has piecewise segments, like this one, break up the integral into each individual part to simplify it.